Greetings and welcome to this explainer. As leaders navigating an increasingly complex digital landscape, you're constantly facing an overwhelming deluge of technical information. Well, our explicit goal today is to cut right through that noise with absolute clarity. We're going to build a robust strategic scaffolding for you. Together, we'll master the fundamental architecture of these large language models, but strictly without the math. So, let's proceed. Consider this highly illustrative scenario. A chief information officer is interviewing two candidates for a director-level role overseeing machine learning infrastructure. The first candidate answers a structural question with a massive flood of technical jargon: residual streams, layer normalization, key value caches. The CIO recognizes the vocabulary, sure, but grasps absolutely nothing of substance regarding how the system actually functions. Then, the second candidate takes a totally different approach. They provide a clear, conceptual framework of how the system processes text by weighing the relevance between words. The CIO chooses the second candidate immediately. Why? Because conceptual understanding empowers an executive to actually lead a conversation, to interrogate vendors, and to maintain strategic agility. Pure vocabulary, by contrast, merely obfuscates the underlying operational reality. It's exactly that conceptual mindset we must adopt today. This brings us directly to Section 1, the transformer concept. So what does a transformer actually do? At its highest conceptual level, it takes a sequence of tokens, which you can just think of as pieces of words, as an input. It processes them through a series of uniform mathematical layers, and it produces a probability distribution to predict the very next token. Now, what makes this structure profoundly effective is how it fundamentally operates. You see, rather than reading sequentially, word by word, left to right, like we humans do, it processes the entire input sequence in parallel. This parallel processing capability, combined with the fact that its mathematical layers are highly uniform and repeating, makes the transformer exceptionally amenable to massive computational scaling. It's literally a machine built from the ground up for industrial scale calculation. To truly understand this parallel processing, take a look at how the attention mechanism resolves the word it within a sentence. In human terms, we intuitively know what a pronoun refers to based on the context. The machine, however, isn't paying attention in any cognitive sense. Mathematically, it's computing relevance. Notice how the dark blue cell connects the word it directly back to the word report. The mechanism builds meaning by assigning learned relevances between all positions in the text, completely regardless of the physical distance between them. Whether a pronoun is separated from its noun by one word or 1,000 words, the attention mechanism calculates their mathematical relationship simultaneously. It's an incredibly powerful capability, and it genuinely forms the bedrock of modern artificial intelligence. While visually elegant, we have to immediately bridge this mechanism to a rather harsh economic reality. The cost of attention is exceptionally steep. Yes, it's a learned, flexible mechanism that operates in parallel across multiple simultaneous pathways, which are often called heads. But the crucial point for any executive to understand here is the third bullet: quadratic computational scaling. Because every single token must calculate its relevance to every other token in the sequence, the required computational power essentially squares as the text grows. If you double your input document's length, you don't simply double your processing cost, you more than quadruple it. Consequently, extending the context window to ingest massive documents is an exponentially expensive enterprise, and it will deeply impact your operational budget. Which leads us smoothly to another fundamental question. What exactly is the system attending to when it processes these inputs? Well, it operates on embeddings. An embedding is simply the transformation of raw text into a high-dimensional numerical space. Imagine a sprawling map where a meaning is captured geographically. The model performs its mathematical operations not on English sentences or German verbs, but on these semantic, high-dimensional data points. Words with similar meanings are positioned physically closer together within this mathematical architecture, creating a quantifiable topography of human language. We really must elaborate on the strategic business utility of this concept because it's foundational. Since similar meanings cluster together geographically in this multidimensional space, embeddings are tremendously useful well beyond mere next token prediction. Distinct training runs will yield entirely different internal geometries, perfectly tailored to specific data. As an executive, you're frequently going to encounter vendors marketing embeddings as standalone infrastructure products. And why is that? Because they are the underlying architecture powering modern enterprise search engines, sophisticated document classification systems, and hyper-personalized recommendation pipelines. The geometry of this space is essentially a highly structured operational map of semantic meaning that can instantly match a customer query to a relevant product or document. But the true engine driving these modern capabilities isn't merely the architecture itself. That brings us to Section 2, the economics of scale. Consider the empirical scaling laws depicted right here. The horizontal axis represents scale, specifically the volume of training data and the number of parameters, while the vertical axis represents performance. Notice the deeply surprising phenomenon illustrated by these distinct curves. This is exactly what we call capability emergence. Performance on basic text completion, which is represented by the green line, rises smoothly and predictably quite early on. But look closely at the purple and red lines, which represent multi-step reasoning and complex problem solving. They remain completely flat, hovering near zero until a very specific threshold of massive scale is crossed. At that precise juncture, these harder capabilities suddenly unlock. It's effectively a phase transition. Paying for a smaller model often means paying for absolutely zero return on complex reasoning tasks. Which brings us to a stark warning. The trap is taking architectural sophistication as a substitute for the scale that actually drives capability. As an executive, you must absolutely avoid the architecture-only mental model. Vendors will very often emphasize clever architectural distinctions, minor tweaks to the transformer or novel routing mechanisms, to obscure a fundamental lack of raw computational scale. Please do not be misled by marketing literature. A transformer at a small scale remains a highly limited, functionally restricted system. Massive, expensive computational scale is the non-negotiable prerequisite for advanced capability. It's the fuel that makes the engine perform. Having established the theoretical architecture and the absolute necessity of scale, we must now pivot into our resolution phase. Section 3, Practical Strategic Implications. Let's methodically map this architectural reality directly to your business implications. First, because of quadratic attention, expanding your context window to ingest entire corporate manuals or massive legal documents is exponentially expensive to compute. Second, these models generate output strictly token by token. This linear latency means real-time voice, financial trading, or instantaneous customer service applications face severe speed constraints that architecture alone simply cannot magically solve. Third, you must be extremely wary of degraded long context. An advertised limit of 100,000 tokens absolutely does not guarantee reliable reasoning at that extreme length. The model may just lose track of critical information buried in the middle. And finally, the gravity of pre-training means foundational changes to the architecture are rarely feasible for a standard enterprise. You generally have to work with the model precisely as it was originally trained, rather than attempting costly internal overhauls. Now, while the standard transformer unequivocally dominates the current landscape, you will undoubtedly encounter architectural variations in the market. You need to view these not as technical trivia, but as distinct strategic levers. For instance, mixture of experts, or MOE models, dynamically route inputs to specialized subnetworks. This acts primarily as a vital mechanism for cost moderation during inference, because only a small fraction of the model's total parameters are activated for any given word, drastically reducing the required compute while maintaining capability. Then we have long context architectures, which utilize sparse attention techniques to selectively bypass that quadratic cost trap I detailed earlier. And multimodal architectures structurally embed text, images, and audio into the exact same semantic representation space. Look, you don't need to employ engineers to build these systems from scratch, but you absolutely must know their specific capability and cost profiles when evaluating a multi-million-dollar vendor contract. This leads directly to your diagnostic toolkit. During any procurement conversation or strategic planning session, you must demand precise answers to these incisive questions. What is the effective context window for your specific enterprise use case, not merely the theoretical advertised maximum? What is the precise latency profile when deployed at scale? Furthermore, what is the exact ratio of input token cost to output token cost? Output tokens are often significantly more expensive due to memory bandwidth limitations in the hardware. These deliberate questions slice cleanly through the marketing literature and surface the brutal practical implications of the underlying architecture. To conclude our briefing today, I want to leave you with a highly practical assignment. I challenge you to test these architectural limitations empirically yourself. Take a 10-page document. Hide a crucial detail first at the very beginning, then in the absolute middle, and finally at the end. Ask the model to retrieve and reason about it in each distinct scenario. Observe carefully how the system's reasoning degrades depending on the placement of the detail. I highly encourage you to execute this test today to witness these limits firsthand. Ultimately, as artificial intelligence continues to scale, the underlying architecture will only grow more profoundly complex. The real question is your enterprise prepared to adapt its strategy to the brutal mathematics of the machine? Or will you be left paying a premium for an illusion of capability? Thank you for joining this explainer.